Thanks. Hello, everybody. Thank you, AMLD and track organizers for the invitation. My name is Pierre Segonne, and I'm a data scientist working for electricityMap. And I'm going to give you some insights into how we use machine learning within electricityMap to help drive the transition towards a truly decarbonized electricity system. But first off, I will start by explaining what electricityMap is and why it was created, because it's very important to the whole narrative. So first, well, I'm not going to teach you anything by saying that climate change is one of the biggest challenges that we're facing, and that it's mostly the result of us burning a lot of fossil fuels to power our society. And if we want to stop climate change, we know that we have to stop burning these fossil fuels. And it's not easy. It's not easy because, as you can see on this chart, currently there's about 80% of our entire energy supply that is coming from burning fossil fuels. And energy is basically what powers any work that we can do. So it's very fundamental to the way we grow food, heat our homes, or generate goods and services that we consume every day. So if we want to get rid of all these fossil fuels, it kind of means that we have to reinvent 80% of the way we live our lives. But we often serve this, this narrative that the easy solution forward is just to electrify everything. And I'm not going to say it's a bad idea, it's a good idea, but it has to be done in the correct way and with clean electricity. And it's not necessarily the case at all times. A picture can be worth 1,000 words. This is currently the biggest machine that humans have ever created, which is a coal excavator that is used to this day in Germany to extract a lot of coal that is then burned and releases a lot of CO2 in the atmosphere. So that's why electricityMap was created, basically, to create the information layer to drive the transition towards decarbonization of electricity systems. And what we do in practice is that we map the carbon emissions of electricity consumption and generation in real time on an hourly base. And I'm just going to give you a very short demo so it becomes a bit clearer. So if we go here to, so this is the map. If we go to Switzerland, we can see that currently a lot of the power that that Switzerland is consuming is produced by nuclear, a bit of hydro, and then it relies also on imports from Austria and Germany. And with all of that data, we're able to compute that little number that gives how clean the electricity is on the Swiss grid at this moment. So now that we have a better understanding of what electricityMap is, I'm just going to give a few insights into how within electricityMap we use machine learning to achieve our vision. So first off, if we were to draw an analogy and say that we organize decarbonization initiatives on a ladder in terms of complexity and how much reliant they are on machine learning, the first step on that ladder would be granular carbon accounting. So basically, as we integrate more and more renewables in our electricity grids, it creates an inherent variation in the carbon intensity of the electricity on the grid. And you can see here, with this carbon heat clock that is provided by Google, a visualization of that variability. You can see that at the end of the day, here, in North Carolina in September, there was almost no carbon-free electricity on the grid. But at noon, when the sun was shining, the grid was almost completely powered by clean electricity. So this creates a real need to do accounting of carbon emissions on an hourly base. And this is where electricityMap comes in, that can provide the hourly carbon intensity figures that are needed. In practice, we work with big customers like Google or Microsoft and others, and they have a requirement for having data for every hour of the year. But the problem is that the data sources that we rely on sometimes go out. So we have to build models, machine learning models, that do compute estimates for these carbon emission figures when there's no data available. So we have gap filling algorithms that basically use the periodicity of the electricity grid to compute weighted averages using like the same time of the day from weeks, months, and years apart to estimate what the carbon intensity of a missing daytime would be. And, and because our customers also have a global coverage, there's a need to generate these hourly figures and data for places in the world where that data just doesn't exist. And so this is an example of what we did in Korea. We were able to gather some aggregate monthly data that was broken down into production mixes, and some hourly but very lagged data to train a model that would generate hourly estimates for the production mix in Korea. And now you can see on the map that what is the estimated production mix in Korea at all times. And typically we see through these partnerships that that granular carbon accounting unlocks interesting pathways for emission reductions. This is, for example, the carbon footprint tool that is now available on Google Cloud, which provides estimates of the carbon emissions related to cloud usage to all of the users of Google Cloud. And this is actually the carbon footprint of running electricity map on Google Cloud. And we use that to pick the data centers and regions in the world that are the cleanest, and also the technologies that are cleanest to reduce the overall carbon impact of running electricity map. So if we go up the ladder now, on the second rung, we would find demand-side response, which is a bit more complicated. But the idea here is to use forecasted carbon intensity signal to dictate what should be the consumption behavior of electricity-intensive applications. And we do this basically by predicting in the next 48 hours what the carbon intensity is going to be in a bunch of different zones in the world. And the way we do this is by, for a given zone, we would look at weather features that we would complement with autoregressive features and seasonal features. And we would concatenate that with these same features, but for all the zones neighboring it, etc., and pass this through a regularized linear model that selects the best features to then predict the next 48 hours of carbon intensity in a given zone. And this has very interesting applications, as Google is using this to shift the load on their data centers. So as you can see here, the green line is the carbon optimized load that they do, and you can see that the load reduces in the middle of the day if the carbon intensity is the highest, and they shift that consumption to other times where electricity is greener, which has huge saving potential. And we also provide these kind of smart adaptation of behavior for individual consumers. So you can see on the left, this is the app of CEAS NVA, which is like one of the the Danish electricity providers, and they provide to their customers forecast of what the consumption mix will be, so that individuals can also adapt their behavior in their homes. Most importantly, the next version of Windows will most likely also use our data to update automatically at times where electricity is the greenest for where the computer is located. And we envision that in the future, this kind of smart behavior will also be adopted for the charging of electric cars and for running automatically like electricity-intensive appliances. And finally, on the last rung of the ladder, which is still something that is that is not functional, but inspirational rather, is assessing the impact of large-scale decarbonization projects using long-term marginal emission factors. So basically, the idea here is to train a machine learning model that would be able to predict where is it optimal to install a new wind power farm, for example, and what the impact of that would be. And I'm mentioning this because we currently have some linear models that do generate short-term marginal emission factors, which answer the same question, but with the strong assumption that the grid configuration doesn't change. And we've also seen recent papers that are supporting that claim. I think I'm running out of time, so that's it for today. Thanks a lot for your attention. And just a quick self-promotion, we are hiring. And we also have an open source repository where hundreds of contributors from all around the world, help us increase our coverage and the precision of the data we provide. Thank you.